Chapter 7 Ionic Equilibria. In this chapter, we have another 3 subtopics: 7.1 Acid and Bases, 7.2 Acid-base titration, and 7.3 Solubility Equilibria. 7.1 Acids and Bases, Part 1. There are two definitions for acid and base. According to Arrhenius, acid is a substance that dissociates in water to yield hydronium ion. For example, the hydrogen chloride acid will dissociate in water to produce hydronium ion H+, and chloride ion Cl-. While base is a substance that dissociates in water to yield hydroxide ion. For example, sodium hydroxide will dissociate in water to form sodium ion Na+, and hydroxide ion OH-. Referring to Bronsted-Lowry, acid is any species that will donate the proton H+ ion. For example, the acetic acid will donate the proton H+ to water molecule and form the acetate ion CH3COO-. So, acetic acid as a proton donor is an acid. In contrast, the Bronsted-Lowry base is any species that accept proton H+ ion, and they must have the lone pair electrons to bind with the hydronium ion. As an example, ammonia will accept a proton H+ from water molecule and form ammonium ion NH4+. So, ammonia as a proton acceptor is a base. Conjugate acid-base pair. From this equation, could you identify the Bronsted-Lowry acid or Bronsted-Lowry base? The Bronsted-Lowry acid is water because it will donate a proton H+ ion to form hydroxide ion as its conjugate base. Ammonia will accept proton from water molecule, so ammonia is a base, and the product form ammonium ion as its conjugate acid. When the Bronsted-Lowry acid releases proton, the resulting species is conjugate base. And when the Bronsted-Lowry base accepts proton, the resulting species is conjugate acid. So, from the above equation, we can say that the ammonia and ammonium ion as a conjugate acid-base pair. And the same thing goes to water and hydroxide ion. In chemistry, pH is a scale used to specify the acidity or basicity of an aqueous solution. pH are defined as negative log concentration of hydronium ion. We also can find the concentration of hydronium ion by antilog negative pH value. So, we can relate that the higher the concentration of hydronium ion, the value of pH becomes smaller. pOH is a measure of hydroxide ion's concentration, and it is used to express the alkalinity. The formula of pOH is negative log concentration of hydroxide ion. While to find the concentration of hydroxide ion, we also can antilog the negative pOH value. So, the higher the concentration of hydroxide ion, the lower the pOH value, the higher the pH value. Auto-ionization of water. Water undergoes auto-ionization according to the following equation. In pure water, the concentration of hydronium ion and hydroxide ions are equal to the value of 1.0 times 10 power of -7. The equilibrium expression for the above reaction is written below as Kw equal to the concentration of hydronium ion times concentration of hydroxide ion, and at 25 degrees Celsius, the value of Kw has been determined to be 1.0 times 10 power of negative 14. Water molecules are amphoteric and can both act as an acid and a base. In the process of auto-ionization of water as shown on this slide, one water molecule acts as an acid, which is a proton donor, while the other water molecule acts as a base, which is proton acceptor. In pure water, the concentration of hydronium ion and hydroxide ion are equal. By substituting the value for hydronium ion concentration and hydroxide ion concentration at 25 degrees Celsius into Kw expression, we get the value of 1.0 times 10 power of negative 14. If we know either one, concentration of ions, by using this Kw expression, we also can find the other species concentration. For example, concentration of hydronium ion equal to Kw divided by concentration of hydroxide ion, and vice versa for hydroxide ion. A change in concentration of hydronium ion will cause an inverse change in concentration of hydroxide ion. Example, the higher the concentration of hydronium ion, so we can get the lower value of concentration of hydroxide ion. And the higher the concentration of hydroxide ion, we will get the lower concentration of hydronium ion. Equilibrium constant for this reaction is called as ion product constant of water, Kw, and is defined as by multiplying the concentration of hydronium ion and concentration of hydroxide ion, and resulting the value of 1.0 times 10 power of negative 14. From this Kw expression, if we negative log for both sides, we will get pH plus pOH equal to pKw. Since we know the Kw value is 1 exponent 10 negative 14, so we can get pH plus pOH equal to 14. The relationship between concentration of hydronium ion and hydroxide ion and the relative acidity of solution. If the concentration of hydronium ion and hydroxide ions are equal, we can say that the solution is neutral solution with the value of pH equal to 7. If the concentration of hydronium ion greater than hydroxide ion, the solution is acidic solution and the pH value less than 7. And if the concentration of hydronium ion is less than hydroxide ion, the solution is basic solution with the value of pH greater than 7. That's all. Thank you.